Okay, if we have a function that is continuous in a compact set, then f will be uniformly continuous in that set, right? In that domain. So, how can we prove that statement? Let's, of course, start with the epsilon greater than 0, that we have this given as a value, as an input. Then also we know we have the assumption that f is continuous on D, and that's basically have a meaning, right? Basically we will have that for every epsilon we will have a delta function for each point of the domain that exists, such that we will have the neighborhood that map 1 to 1, right? So this is what I said. For each x in the domain, there exists an epsilon delta, right? That is greater than 0, but this delta is depending of the point in x, right? This is why I have the little x here, because it may change. I mean, if the function is changing, we may need a different delta for each point, right? Such that we will have that for every x and y, right, who make this difference, the evaluation of the function, the difference of the evaluation of the function less than epsilon over 2. Why over 2? This is because basically we will have a neighborhood for x and a neighborhood for y, and we will use it later, and you will see how we can use that. But yes, let's look for just whatever epsilon you have divided between 2, and still because it is continuous, it will work for every number, so we can have that. Whenever the difference, the distance between these two numbers in the real line will be less than the delta x, right? This x depends on this x, and y also is inside of the domain. Okay. Now what? Now we have a family of neighborhoods. We have that for every x in the domain that is a compact set, we will have open set. An open set, basically a neighborhood is, we can say it is an open set, an open interval that will go from the point x to all the way to delta x over 2, right? So we will have something like this. This is the real line that we have for every single xi. We say xi because we have infinitus x here, right? We have a neighborhood, right? It's an open interval. Okay. Now what we know by the statement, the definition of the statement, that D is a compact set, right? So what it means, all this family of neighborhoods will be, of course, an open cover of D. And because D is a compact set, we can ensure that we will have a finite subcover of D covers, right? In other words, there exists a finite number of x I from 1 to n in the domain, such that if I union all the neighborhoods of that we create for these values, we will cover still all the domains. So basically the domain, the closed interval, will be a subset of this union, right? So what we can do is we can assign to this delta to be the minimum number, right? The minimum of all these deltas, get the minimum, right? And then we can try to prove if that minimum will work, right? Let's suppose that we have these x and y's in D. We have that they will be, the distance between these two will be less than this minimum, right? Then x will be inside of this neighborhood for some I, doesn't matter which one, but you just choose one and it will work for some I amount of this n, right? And then it will say, okay, I bring this from the previous page. Okay, then what? Well, let's see here in the picture. We have the xi somewhere. We have the open set. We say that this x will be part of this open set, of this neighborhood, right? Then we claim that the distance from this y that we have here and the xi in this part, it is basically is this. We have an x in the middle, so we can add and remove this x. Basically, we insert a 0 here, right? But by the triangle inequality, we can separate this by the addition. And we say that by the assumption this distance is less than delta, right? And also this other one, that is the distance from here to the x, it is less than delta xi over 2, right? So we will have it here. But also this is less or equal than if I duplicated this delta I, right? Because this delta is the minimum of all the deltas. So if I selected the same delta, it could be the same because it could be the minimum, or it could be a little bit greater than the other one, the minimum of the deltas, and they will be still greater than the whole distance that we are looking for, right? So because we have the half and a half, basically we will have the delta xi. So we can say that the distance from y to here is less than delta xi. And by the assumption, this assumption is that any x and y that we have will be less than epsilon over 2. We saw this at the beginning. We assumed that, right? Then we ensure that this is correct. In the other hand, we have also the x that is part of this neighborhood, and we need to prove that this x and the distance from here to here is also less than the epsilon, the delta x over 2. But if it's the half, it's also less than the whole value, right? Therefore, I can also conclude that the distance between the evaluation of the function between x and xi will be also less than epsilon over 2. Then we can get basically the distance, the whole distance from x to y directly. It will be from, basically we add this in the middle again, this 0, right? And we separate it with the triangle inequality. And what was that? This was epsilon over 2, and basically it will be equal to epsilon. Therefore, f is uniformly continuous. By the way, another thing that we should contemplate here, if f is uniformly continuous in an open set, right? Then I will say here, then if the open set could extend to a closed set, right? A comma b. Let's say open set a comma b, right? We can extend that. Also, if we can extend the open set, what I mean with the extend on open set, if the limit, right, let's say x tend to a f of a exists, and the limit of x tending to b of f of b exists, basically if that happens and the function is continuous, then I will say that also f is uniformly continuous. That is another theorem that we can prove also, but I just will say it because it's useful in many cases.